Hey, OChemStars, this is Mrs. Vandeloy bringing you more OChemStar video. We are in Chapter 3, Section 6. We're still talking about alkenes and alkynes, don't you worry. And this section really begins a kind of long section where we talk about different kinds of reactions with alkenes and alkynes. These are much more reactive than alkanes were. And the reason being is that the bonds are unsaturated. We have those electrons, which are reactive species, right? So we are going to discover there's a lot more to the reactions of alkenes and alkynes than we do with alkanes. For really what we're going to do in this section is that we're going to compare the alkanes, what we learned in Chapter 2, with the new things with Chapter 3, with the alkenes. So let's kind of review what we learned in Chapter 2. Alkanes can undergo certain kind of reactions. The first one we learned was combustion. Alkenes can undergo combustion as well. So what is a combustion reaction? You form carbon dioxide and water, okay? We learned about halogenation. We can add a halogen, fluorine, chlorine, bromine, sometimes iodine, to an alkane, and we did it by substitution. And we said substitution is a swap. Did you write down that word swap by a substitution? I made the analogy that if you are the star of your sports team and you're just scoring so many points that you're embarrassing the other team, perhaps the coach will pull you out and put someone who normally doesn't play in for you because you're going to win the game no matter what, right? We call that a substitution. The star leaves, the bench person joins, okay? It is one leaves, one comes in, and that's what we said happened with alkanes. That the hydrogen, let's look down here, that the hydrogen of the alkane leaves and joins up with B, and the A joins the carbon group, okay? Write this down. You have two products. Remember that from Chapter 2. Big deal, because we're going to find out with alkenes that atoms are added to the alkene, and write this down, you only have one product with addition. So that's an easy way to remember, to tell what you're dealing with. Substitution has two. Halogenation with alkenes are added, you have one product, okay? So let's see how this works. So this is in general what's going to happen. So here's my alkene, and here one of these is going to be a halogen, and we're going to see where both could be a halogen. But for right now, let's make our life a little easier and call B the halogen and A not. Why are halogens such a big deal? Because if you recall, fluorine and chlorine are highly electronegative. They have greater control over the electrons in that bond with A and B. It's like that chocolate analogy when I asked someone to help me out. So that would be a good example why I need halogens, because you're already starting off an imbalance. Okay, so now I have a partially positive A, and we're going to teach you a new term that you're going to get to know. It's called an electrophile. That Greek root, philios, means loving. Okay, so Philadelphia is literally meaning the city of brotherly love. Okay, so what is an electrophile? It is a species, it is something that literally loves electrons, electron loving. Well, which one of these two terms is now electron loving? It's going to be A, because it's partially positive and opposites attract. Why isn't it B? It's highly electronegative. It already has the electrons close by that it wanted. All right, it doesn't want any extra. It already grabbed those from A, leaving A a little bit void. Okay, so now A is looking for electrons. Okay, well, where is it going to find electrons? Well, where are there lots of electrons? And I said, well, like 4 to be exact. You guessed it, right here. There's 4 electrons in that double bond, bringing a highly attractive A to its proximity. Okay, so what's going to happen? So I broke this down step by step. So I'm going to start here. A is attracted to that double bond, okay? Oops, bring this down a little bit. There we go. So A is attracted to this double bond. So here it is. Woo, look at. Oh, it's getting all excited. I'm going to do something else here. Ready? Look at this. So now look what A can do. It can go right in there. Look at those electrons. Okay, so it's highly attracted to that double bond. So what is it going to do next? A is going to grab one of those electrons, or maybe, whatever, two electrons, depends if A is completely void. So it's going to grab some electrons, breaking that pi bond. All right, so now A is fully, bonded to one of the carbons, but by taking those electrons off of the double bond and making its own sigma bond with that now, it's leaving the other carbon void, okay? So now what's going to happen? B, once A breaks away, it is totally said, here, you take all my electrons. I don't want them anymore. I got my own electrons. So it gave B its electrons. So now B is a fully charged negative ion. So what's going to happen? This B, here's my carbocation. Do you see where that word comes from? Here's this carbo, meaning carbon, cat ion. Do you hear me enunciating? That T in cation is your positive charge. So now what? B is fully negative, and it's going to be attracted here. Remember, B has its own electrons. It doesn't need any from the other carbon, all right? And so what can it do now? It can actually bond with that carbocation, and so both things are added to the double bond. So you break the pi bond, and now you have all single bonds. You are creating an alkane by this addition. You might want to write that down. You are creating an alkane by this addition process, okay? Let's go on to the next page when you're ready. So section 3.7 is about the polar addition reactions. And polar means usually I have highly electronegative things to make a polar situation. That's your partial positive, partial negative. So let's talk about the addition of halogens. And you're like, Mrs. Vanderwaal, chlorine is not a polar molecule, it's a nonpolar molecule, right? Because even though I have a big 4 here, it's completely identical. And you know what? You are exactly right. I get that. But what's going to happen here? Right, here's my chlorine. And as this chlorine molecule gets closer to here, what's going to happen? There's going to be an instant dipole, is what they call it, an instant dipole. Those electrons, those 4 electrons right here, are going to cause a repulsion. And the chlorine that is closest is going to have its electrons shift away, creating an instantaneous partial positive, partial negative. So then it sets up just like we did in section 3.6. So even though this chlorine molecule is a nonpolar molecule, if it gets close to these 4 electrons, the chlorine's electrons are going to be repelled, causing it to shift to the other chlorine, causing a partial positive, partial negative. So let me kind of show that right now. So this is kind of what I was trying to show you, all right? So that's the instantaneous dipole that is created by those 4 electrons in that double bond. All right, so now what's going to happen? Just like what we did before, all right? We're going to have a what setup? We're going to break that double bond. All right, and then the first chlorine, this is your partial positive chlorine goes there, creating the carbocation, which is going to attract the negative other chlorine. So there you go. How many products do I have? 1. All right, and that's true for addition. So then what? Let's name it while we're at it. How am I going to name this? This is an alkane. You know how to name it. Go ahead and do that. Okay, this is what I got, 2,3-dichlorobutane. Now, am I only allowed one double bond? No, if I have a ratio of one of these dienes and two of my halogens, yeah, this is going to work. So once again, what's going to happen here? I'm going to do what? I'm going to end up breaking those bonds, as long as I have enough of the bromine. So I have what, 5 carbons here? Oh, so then why'd I put 6? That's kind of silly, isn't it? Okay, there you go. So then what? I'm going to break the double bonds and I'm going to put bromines in here. 1, 2, there, that's where the first double bond is. And then I'm going to put another 1, 2 right here. So once again, how many products do I have? I only have one product. And how am I going to name this? 1, 2, 4, 5 tetrabromopentane. Wow, that's pretty cool. Hey, let's go on and let's look at problem number 1. So write an equation for the reaction of bromine at room temperature with 1-butene. So what should you do first? Maybe, just maybe, you should write out what 1-butene even looks like. Go for it. Okay, this is what I got. So what's going to happen? I'm going to take one of these bromines, and it's going to be breaking the bond, hop it on here, forming a carbocation, and there you go. One product. How do I name it? 1,2-dibromobutane, okay? Try the next one. Try cyclohexene. Okay, so here is cyclohexene. Remember, you have to have that double bond for this to work. I'm going to add bromine to it, and there's this. And so now what? That bromine is going to break the bond, so I have a cycloalkane, and the first bromine is going to go on one of the double bonds, and the second one's going to go on the other double bond. So what would that be? It's 1,2-dibromocyclohexane. So problem number 2 says, well, how is this reaction different from the halogenation of alkanes? Let's kind of review. Here's my cycloalkane. I just kind of use a similar idea. And bromine, the first difference is that I needed UV light. Okay, I needed UV light forming free radicals. Do you remember we talked about that in chapter 2? So that UV light will break the bromine-bromine bond, forming a free radical. So the bromine will go and chase after, the carbon and the hydrogen and things like that. So what happens? One bromine gets attached and the other bromine gets the hydrogen. So how is this different? Addition, both things jump on the double bond. Here, only one thing jumps on and something jumps off. Here I have one product, here I have 2 products, okay? So let's check out the next page. So we said this is the polar addition. So how about introducing to you a polar molecule? Well, what comes to mind will be water. So if an acid catalyst is present, so I will talk about that as an H+. This is my acid catalyst. And if you recall from maybe your biology class or maybe even your chemistry class, a catalyst will speed up a reaction without actually being part of it in a sense, all right? I will use up the H+, but then I will reuse or remake it again. So it actually doesn't show up on the equation. But then water, and look how I wrote water. That's an odd way to write water. This is hydrogen hydroxide, right? Why would I do that? Because I want to show you the OH is your partially negative, making one of the H's your partially positive, okay? So it adds as HOH and the products are alcohol. So what's an alcohol? Again, you should be, kind of thinking about your front of your section there where you have those functional groups. Alcohols are OH groups on a carbon, okay? And don't worry, we're going to talk a whole lot more about alcohols next quarter, okay? And a lot of chemistry with that. So anyway, so start getting used to, we're going to be talking about alcohols actually quite a bit throughout this whole course. So just know OH is an alcohol. Now it says neutral water is not acidic enough to provide the protons to start the reaction. All right, so it says the mechanism will be actually discussed later, but just for right now what happens, I need an acid catalyst. All right, so this starts the whole ball rolling. So what do you think the acid is going to be doing? Hey baby, look at that. All right, so this is going to break the bond. All right, and it's going to jump on that, forming this what? Carbocation. And actually what happens next, that here comes the water. Now, which end of water is going to be attracted to the H, or to the carbocation? Well, it's the oxygen part, maybe in a sense the hydroxide part. And so it's flipped it upside down because that's where the attraction is going to go. And so right now, if you look at it, this oxygen has, once it bonds with the carbon, has 3 bonds. Folks, when we did the intro, I really tried to impress upon you, in a neutral molecule, oxygen is only going to have 2 bonds. Right now, we're forming 3 bonds, so 1 bond has to go. Well, here is what I have left, and it boots off the H+. So here I like rejuvenated my H+. I started out with my acid catalyst, all right? So I started off my acid catalyst. It breaks the bonds, jumps on one of the carbons, forming a carbocation. Whoops, I moved the H actually. All right, forming the carbocation. It's attracting the O of the water, like the OH really. So the O bonds, booting off the H+, so it could attack another double bond. So that is, in a sense, a mechanism. I kind of gave you a prelude to that. We'll talk more about that later, but what is my end result? H ends up on one carbon, OH ends up on the other carbon. You broke the bond. So why don't you try cyclohexene plus water? Go ahead and do that. Pause this, try it on your own. So this is what I got right here. So here's my cyclohexene. Here's my water. I wrote it as HOH. And you break the bond and you put an H on one and the OH on the other one. How would I name this, by the way? We haven't really been practicing our alcohol names. This would be cyclohexanol with an OL at the end. This would be ethanol, F because it's 2 carbons with an oxygen at the end. So let's check out problem number 3. Why don't you pause this and do the 2 of these, and then when you're done, come back. So we'll see you shortly. Bye-bye. So this is what I came up with. There's my cyclopentene plus water to make cyclopentanol. I have my 2-butene plus water to make 2-butanol. Okay, and there you go. All right, so let's look at the third section here, the addition of acids. Do you remember when we did the water, we needed an acid catalyst to make this reaction work? Well, if you start off with an acid, you don't need an acid catalyst, it will just do it on its own. So a variety of acids are going to add to the double bond of alkenes. The hydrogen ion, the proton, is your electrophile. Throw that little word back in again. And that adds to the one carbon of the double bond, and the remainder of the acid becomes connected to the other one. So for example, here's my HA. This is your proton of the hydrogen ion. Here's the rest of the acid. Breaks the bond, the H jumps on one, the rest of the acid will jump on the other one. So let's look at a specific example. So I'm doing this, I'm assuming that, these are hydrogens. Really, they can be anything, all right? But I just made them hydrogens because it's a lot easier to type that way. So I break the bond when the H jumps on and the chlorine follows suit. So there's where the chlorine goes. So that would be chloroethane, okay? Well, what about the next one? Let's check this one out. You have cyclopentene plus sulfuric acid. Sulfuric acid, you might recall, is H2SO4. Remember, I ate something icky, all right? Sulfuric acid, I had my sulfate ion. And what I drew for you is the Lewis structure for sulfuric acid. I know it looks odd. It does not obey the octet rule. Excuse me, I was yawning. The octet rule. So you do have two oxygens with double bonds, but you have two oxygens that has the two hydrogens on them. Why am I showing you this? Because which oxygen, the double bonded or the single bonded oxygen, is going to attach to the carbon chain? Well, pick a hydrogen and that's going to attach. So it's the the oxygen that the hydrogen originally was attached to is going to jump on that. So what do I mean by that? Well, here is my cyclo pentane. I moved the hydrogen here. It's easier to draw that way. And this is where the rest of it goes. So notice was the original bond. That's what broke off. And so this becomes part of that acid, okay? So why don't you go ahead and take a few minutes out and please do problem number 4, and then we're done with this video. All right, welcome back. This is what I did. So I broke the bond, put the hydrogen on one, the iodine on the other one. Now, can I ask you something? Could I have done this instead? What do you think? The answer is sure. How would I name this? 2-iodobutane. Okay, how would you have named this? 2-iodobutane. It's the same thing, isn't it? Okay, and then finally the cyclohexene and hydrobromic acid. Here's my cyclohexene. Break the bond, the H goes on one, bromine goes on the other one, so it becomes bromocyclohexane. And there you go. So addition really isn't that difficult. You break the bond and put the stuff on it, and there you go. Don't wait to be great. We'll see you next time. Take care. Bye-bye.